Hi Rebecca, how are you? Okay, so today we are going to talk about the. Okay, tell me one thing. Duhamel's principle is clear or not? If I it is clear, yeah. So this is the most important thing. Like if you are studying the heat equation, you don't know anything. You just know this Duhamel principle, how to proceed with the Duhamel's principle. Then your um, study of heat equation is successful. This is the most important thing. I think if you are gonna mention that you have studied the heat equation problem, then one can ask, so tell me about the Duhamel's principle. I am going to give a very short description just to remind. So what is the Duhamel principle? We have a non-homogeneous set of system, a non-homogeneous heat equation, ut minus Laplacian of u equals to this f, and we have a homogeneous boundary condition or homogeneous initial data. It was an initial data or boundary condition, Roberto. It was initial data or boundary condition. Initial condition, है ना? Initial condition. It was initial condition. I don't remember. I'm just asking you because I'm trusting you blindly. It was initial condition, yeah. So ux comma 0 equals to 0. This homogeneous initial condition. So what we did, we transform this another problem u tilde t minus Laplacian of u tilde is equals to 0. And in that case, this initial condition reduced, homogeneous initial condition reduced to the non-homogeneous initial condition like this pass to F. So what was the main idea behind the Duhamel's principle? That suppose if u is the solution of this equation and u tilde is the solution of this equation, then u is nothing but the integration of u tilde over t, isn't it? This was the Duhamel's principle. It means you need to remind yourself the procedure, but what is the consequences, what is the main idea behind the Duhamel's principle that you should know. Integration was 0 to t, yeah. So 0 to t. So u is u tilde ds, like we are taking s, and this was Duhamel's principle. So u tilde is the solution of this equation and u is the solution. So there is a relation between u to u tilde. In every book, the main idea behind writing the Duhamel's principle is that the integral of the solution of a homogeneous equation is the solution of the non-homogeneous equation. The integration over time of the solution of the homogeneous transformed homogeneous transformed. So you need to keep in mind this is the transformed equation of the given non-homogeneous. Homogeneous, because if you will not be transforming, then this f is not going to be same. You have to transform this to get this. So homogeneous transformed heat equation is the solution of non solution of given non homogeneous equation with zero initial data. So this was the case. Even in the boundary condition, you will be getting the same. So this is the Duhamel's principle, and how we proceed. You know the procedure. We have solved this in you. So every time, just keep this four line in your mind. Just. and you're gonna solve that. Because the Duhamel's principle till the date is going to be asked at the very big level, like suppose you are appearing for a PhD exams, so one can ask you write and prove the Duhamel's principle. Next, let's talk about the parabolic cylinder and second order linear parabolic equation. So heat equation is elliptic, parabolic or hyperbolic. Hmm? Heat equation is elliptic, parabolic or hyperbolic. Please tell me. Hmm? Heat equation is parabolic, elliptic or hyperbolic. Sorry. Yeah. So no, it is parabolic. Yeah, it is parabolic. I was just looking for the proof where I gave this. So this was the case where I written that heat equation is parabolic and you derived it. Um, I like this is your notes. I was just looking for the notes because you cannot say that you don't know. I haven't mentioned. So this is the notes. So if you, this is the heat equation and B square minus 4AC. So suppose if you are talking in one dimension, so ut minus uxx equals to 0. So the coefficient of utt is 0. The coefficient of uxx, a is 0, c is minus 1. So b square minus 4 and b is the coefficient of utx, that is 0. So the b square minus 4ac is going to be 0, so it is parabolic. Always keep in your mind, I did not want to do that. You should remember how we are deriving the parabolicity because we are going to talk about the regularization problem. So how the regularization problem is going to work, I will not show you numerically because numerically it has its own importance. Dealing with a parabolic equation is much easier than dealing with the hyperbolic equation. So always keep in your mind. I was expecting that you are aware of this. Actually, I have learned those things. So for me, I just have learned that Laplace is elliptic, wave is hyperbolic, and heat is parabolic. Sometimes even I don't know how to write the proof. So, so we now jump to the, by this week I will be completing the heat equation. I have just to write the weak maximum principle, strong maximum principle, Wilder's theorem and regularity. Just today I will be completing weak maximum principle and strong maximum principle, and I will give you the mean value property as a homework because I already have proved the mean value property, how to take the spherical mean. So here you will not be taking the spherical mean, rather you will be taking the cylindrical mean. Yeah, sure. Mm-hmm. I am not getting your questions very clearly. Can you please repeat? Okay. So you are saying that the initial condition is taken to be only zero, or you can take some fixed value x comma t naught. Yeah, you can. Let me give you a reason behind this. I understand your Spanish. This was the first time I understood the Spanish. So you are asking that why we are taking only zero initial condition. So the reason behind is that suppose you take a rod, don't just think it physically. Suppose you take a rod. The rod is uniform, like there is no heat, nothing. Basically, when we talk about the heat equation, we assume that we are starting to give this a temperature at this point. We are started to heat this rod at this end, and then the heat is trying to distribute in the whole rod. We are heating this rod at, suppose this is A end and this is B end, at the end A, and the heat start to distribute over the rod. Now the idea behind taking the initial condition t equals to 0, we assume that before before heating this end, the time is 0. You can measure it like, oh, we started to work at t equals to t naught. Before that we were not heating it at, but at t equals to t naught we measure the condition, we measure the temperature of the rod, and then at this time we started to heat, this rod. So at that moment you will take the condition ux comma t naught is something 0, because at the time t naught the heat is 0, because we haven't given any temperature to this rod. So this is just for the sake of convenience. You can take t naught, it doesn't matter at all. Is it clear?
Yes, teacher, thanks.
Okay.
I have a little question. The function f is function of x and the spatial variables, or can be a function of u, for example, like a reaction diffusion equation.
Which function this f?
F, yeah.
So there is a way to write this function f. If you will be writing that this function f is function of u, suppose.
Mhm.
So you can just let me write a single equation to show you. Suppose you write ut minus ux. Tell me a function, any function,
U square, for example.
u square. In that case, you will be writing del over del t minus del 2 over del x square. Just pass this minus u identity u is equals to 0. Can you write this? This is a homogeneous system, isn't it? To make it non-homogeneous, what you need? That this should be free from u, isn't it? So here, to make it non-homogeneous, it should be function of x comma t. Now, suppose you have some trigonometric function or you have some different kind of function, so we can make a setup to pass on this time. Like if it is a sine function, so what is the extension of sine? 1 minus
U.
u minus sine 0 is 0. So sine
Minus U
minus,
to the power 3 over 3.
so again you can pass this, but when it is a cost function, it will be a non-homogeneous, isn't it? So you have to analyze this source term very, like a very keen observation. You have to make a very keen observation. If it is a sine function, then it is going to be homogeneous. But if it is a cos function, then still one will be left. You cannot deal with this one. we know that when we have a Laplace equation, then it is very difficult to solve the Laplace equation. So there are not a number of questions based on the heat equation, but I will try to put some question based on the heat equation in your assignment so that you can solve them and you can get the answer how we are solving. Like with the method of separation of variable, there is a way to solve the heat equation. That is the method of separation of variable. We now jump to the study of an important property called the weak maximum principle satisfied by the solution of general second order linear parabolic. Can anyone tell me why I am saying that second order? This is a very important question. Why I am saying that second order? This is your test project of mind.
Because it has derivatives at second order, right? The spatial derivatives.
Sorry.
Because that equation has a second derivatives. Yeah.
No, why when I am talking about mentioning the maximum principle, why I am saying that satisfy the solution of general second order linear parabolic equation. If it be with third order, then what kind of difficulty will arise? Do you remember when we were discussing the hyperbolicity, parabolicity and ellipticity? So what I said that if you have third order, then you will take a canonical transformation to make that third order PDE to second order, and then you have to check B square minus 4AC. Another, you cannot check its parabolicity. So that's why when we are talking about maximum principle or minimum principle, we have to deal with the second order linear equation. In that case only you can check this. And even when you have a general second order linear equation, again you have to apply the canonical form to make it up to two variables, to make it up to two spatial variables. One spatial and one time variable. Another you cannot change this. So when we are proceeding with the number of order or when we are proceeding with the number of variables, it is very difficult to check the parabolicity. To check this condition, we have to be only with the two independent variable. When you will have two independent variable, then you can find this coefficient. If you have more than two independent variables, you cannot find this. So whether I am writing a general, for the sake of convenience, we know that this is going to be heat equation, but when you prove that this is a parabolic or this is a hyperbolic, you reduce it to the using the transformation of the variable, like x t will be transformed to xi and y t will be transformed to eta. Parabolic cylinder and second order linear. Let's define some notation so that we can use that notation. I will write both the notation from the book of Evans, and I will also write the notation which I am using. You can get any of the notation. We assume omega. In the book of Evans, he is taking u at the place of omega. Is a bounded open setting Rn. So omega is contained in Rn. If you are saying that u, then it is contained in Rn. We assume omega is a bounded open set in Rn, and we fix a time t, we fix a time t like a bounded time. We are not good. T belongs to open interval 0 comma infinity, isn't it? But we are fixing that this t is belong to 0 comma t. This is a bounded time. What happened, Roberto? Why? What happened? Is there something wrong?
No, no. Oh, no, it's right.
You were smiling, so I thought. Now consider the parabolic cylinder. If you have doubt at any points, then please do ask. Consider the parabolic cylinder, omega t. In the book of Evans, he is writing ut, defined by omega cross 0 comma t. This is the collection of those spatial and time variables such that x belongs to omega and t belongs to 0 comma t. This is the parabolic cylinder, and how does it look like? There is a reason why we are calling it a parabolic cylinder. You can relate to this. What is the form of this rod? If you are seeing it in a 3D, then isn't it is a cylinder? But like if you take a rod and you are taking that rod in the current atmosphere, so this is basically a cylinder, isn't it? In 3 dimensional. So just consider this. I am just going to portray this horizontal rod to the vertical rod. Just so this is 3 dimensional. I will tell you why the surface of why the bottom and the upper of this cylinder is not circular, because this is not, they are not taking a circular cylinder. The cylinder can be of any form. If it is a circular cylinder, then this will be like this, isn't it? But it is not always the case. It can be circular or it can be of any surface. It is a cylinder, but it is not circular. It might be like a rectangle, or it might be at some point it is thin and at some point is expanding. Just imagine, can you imagine this thing in your mind? So just label like when we take the cylinder and we are taking the bottom of that cylinder and all these points, so this omega or u is the inner region and the boundary is this region, like this and also the boundary of its surface. It is very difficult sometimes to explain the geometry, but I think you are getting it. So, like the boundary might be the walls of the cylinder, and when we are talking about its surface, then the outer area of that cylinder, and we call it omega t. And when you are saying that you are heating this rod, so in which direction T will vary? If you are heating this rod, so in which direction T will vary? This direction? You are heating the rod at this position and then the temperature is increasing in this direction, isn't it? T and X and Y. So in this one, where T will vary? In the upward direction? because you are hitting the rod at this end or at this end, isn't it? So where T will vary with which axis? This or this? At which axis T will vary? This or this? Upward direction. So this is the direction of T. Everything is related to the same one-dimensional heat equation, so you don't need to worry about. Is it clear, Roberto? Okay. The same figure is mentioned in the book of Evans. You can take a look at that book, but I think if you will see this, like my explanation might be explaining better because they are just mentioned. This is just a way I'm writing both the way, like you need to know both the notation. Oh, sorry. This is the closure of the region, like the inner region and the outer region, isn't it? If you remove the inner region from the closure, so we will be left with the one only the boundary, and this is defined as the boundary in Rn cross 0 comma t, because in time is going to vary the same. On the time is not going to, time does not have an outer region. The outer region is only we are talking in the spatial variable. So that's why del omega cross 0 comma t, because the time is going to vary uniformly. Union omega cross t equals to 0. Now we are defining an operator of the form, and that operator will be a parabolic operator. In what condition we are going to see? Now we consider the second order linear differential operator of the form. Ivan,
Sorry for the late joining. I'm very sick.
what happened to you? Is everything okay?
Yeah, but I'm like in my bed, very sick.
Do you have a flu?
Um, I think it's something like that. But yeah, I will take the class.
Did you take the medication?
Right now I'm not taking anything, but I think if I get worse, I will consider it.
I think you should take the medication because the weather is changing, so that might be a reason. These days, most of the people are getting sick.
Yeah.
Now we consider the second order linear differential operator of the form. So this operator, you know, this is del over del t. We are very interested in this operator here. If this L operator is the Laplacian, if this L operator is Laplacian, so we can relate it simply with the Laplacian. But it is not only here. The author is interested. L is not only Laplacian operator, but it also has some first order derivative of the dependent variable with the first order derivative with respect to the spatial variable. So this is the thing to define the parabolic operator. Ut plus LU, and the LU operator is defined as, earlier L was defined as, like when we were talking about only the parabolic case, so L was defined as the minus of Laplacian of U. But here the L is the combination of the Laplacian and the first order partial derivative with respect to spatial variable. Don't think about this. L has a specific thing that it contains the sum of the derivative, spatial derivative, not time derivative. Only spatial derivative. That is the thing. Minus. According to the Evans notation, what is this? Del 2 over del xi del xj. Isn't it? Who is reading the Evans book at the moment? Are you reading the Evans book, Roberto? Camilo is reading, I know. Okay, then that's great. So this operator L is defined in this way. Now if this Bi is 0 and C is 0, it will simply reduce to heat equationing and spatial variable. It will simply reduce to the heat equationing, and this will give you heat equationing and spatial variable. This means that the continuous derivative of the unknown variable, like they are symmetric. So basically this means that, just wait. What we call this property? Harmonic property? No. What we call this property? There is a name, particular name.
Complete differential.
Complete differential, but there is another.
Exact.
No. I have that name in my tongue, but I'm not getting. There is a particular name for this property. I think Ivan should know, but I think he also might have. So this is the property. When we solve the partial differential equation, we take this property. So this is the symmetricity for the coefficient, but for the derivative we call it a name. I don't remember. Now we have the definition of this operator given by this. We are going to discuss the parabolicity of this operator. Under what condition it will be the uniform parabolic or it will be the parabolic. So let's see the definition of the parabolicity. The operator del T plus capital L is called parabolic in. Now one thing which you need to keep in your mind, that if I comma j I equals to j, like there is only one special variable x, then it was very easy to write the parabolicity, isn't it? When I equals to j equals to x, like there is only one special variable, then you can simply get to know a, b and c. But since there are n independent variables, so there will be the specific condition under which condition you can check whether the given operator is parabolic or not. And what is that condition? So let's have a look. So the operator del t plus capital L is called parabolic in omega t if there exists a positive number or a positive function in x comma t in this domain such that summation I varying from I comma j varying from 1 to n a I j x comma t xi I xi j. These are unit normals. These are unit normal greater than or equals to lambda x comma t modulus of xi square for all x comma t belongs to omega t and xi belongs to Rn. If this lambda xt, this function xt is uniformly greater than a positive quantity, in the domain omega t for some positive constant, lambda naught, we say del t plus capital L is uniformly parabolic in omega. Okay, so this is the definition of the parabolic operator in n dimension. When we are in two dimension, that is one time variable and one space variable, so we can simply say that a ij is going to be 1 and the unit normal will be 1, not 1, like it is going to be a single function a, isn't it? And for sure this is going to be greater than some constant you can choose. If this a function is x comma t stays positive, then it is going to be greater than ax comma t. You can choose this lambda, the same function, and if it is a constant, then that will be greater than 0 for sure. So that's what we were analyzing in one spatial heat equation, and it was easier for us to analyze this thing. But when we are in n dimension, then we have to analyze this thing. I am going to put some questions to see whether the given equation is parabolic or not in your assignment, so that you can use this condition. Let omega be bounded open in Rn and assume the operator del t plus L is parabolic in omega t. Let u is belonging to c1 square omega t intersection c omega t bar. Satisfy ut plus lu is greater than less than or equals to 0 in omega t, that is u is a sub solution of del t plus L. Then maximum of u over the closure of the domain is equals to maximum of u over the boundary. That is the basically maximum principle. But here we are talking about the weak maximum principle because we are including if cx comma t equals to 0 in omega. We also have this condition on c. That was a constant appearing in this L. And maximum of u over the closed region is less than or equals to maximum of u plus the positive value of this if c xt is greater than 0 in omega. But before proceeding to the proof of the theorem, I would like to ask you one question. U is belonging to what is the meaning of this? What is the meaning of this?
U is twice differentiable on the domain, but is once differentiable on the boundary.
The second derivative of the u is continuous on inside the domain and u is continuous on the boundary. We cannot talk about the derivative of u on the boundary. We just know that u is continuous on the boundary. However, its second order derivative is continuous inside the domain omega. Because we have a boundary condition, we might have a boundary or initial condition. Yeah, yeah, it means you guys are doing great in your real analysis. Yeah. Okay. So here I would like to say that there is nothing in the proof of this theorem. I will write the proof, but before that I would like to mention one thing. What is the maximum principle of the Laplacian equation? What is the maximum principle of the Laplacian equation? Do you guys remember?
Yes, the maximum and minimum always reach in the boundary.
Exactly. So the maximum and minimum of a Laplacian always lies on the boundary. The same thing is going to apply here. I will write the proof, but the remark is same. You can see that omega t bar. What is this omega t bar? Omega t bar is the union of omega t and the boundary. Isn't it? So it is saying that even if you are going to take the maximum of that function u is a solution of the given operator, then maximum, if you are taking the maximum anywhere in the domain and its boundary, the maximum will always attain on the boundary. In the case c is 0. And when c is not equals to 0, when c is positive, then the maximum of the positive values will be attained on the boundary and it will always be greater than the maximum of u in the case when c is positive. So let's write the proof. But the idea is same. Because sometimes I feel that even the proof is easy, but it is difficult to trace the idea how we are going to say that. But if you know the remark behind that idea, what is the motive of that, how you are understanding, so it is easier. So fix epsilon is greater than 0 and let V is equals to U minus epsilon T, where epsilon is a very small quantity. Then Vt plus Lv is going to be What will be the Laplacian of v? The Laplacian of v will be simply Laplacian of u because this is the time derivative. And since we know that u is the solution of this operator del t plus l, so ut plus lu will be 0, isn't it? Because u is a sub-solution of the operator del t plus l. So ut plus lu is less than or equals to 0. So we are not simply writing that it is less than, it is equals to minus epsilon, rather than we are writing that it is less than or equals to minus epsilon, because minus and this is also a negative quantity. So for sure this is greater than this one, isn't it?
Yes.
This holds in both cases of A and B above. Now we claim that maximum of V over the region omega t bar is equals to maximum of V on the boundary if C equals to 0 in the region omega t, and maximum of V over omega t bar is less than or equals to maximum of V plus if C is equal to 0 in omega t, because this is holding Vt plus Lv is less than or equals to 0. So from here we can say that if we are able to prove the property of V, then we can simply write it for U, because Ut plus Lv is less than or equals to 0. V x naught comma t naught is equals to maximum of V on the region this for some x naught comma t naught belonging to the domain omega t bar. If this point lies inside the region omega t, then the derivative of x naught t naught is going to be 0, and Vt x naught t naught is greater than or equals to 0, and just wait, I'm explaining it. Non-negative definite in the matrix sense. Hence, Vt plus Lv is equals to Vt minus okay. So suppose x naught comma t naught is a point from the domain omega t bar. That point may lies on the boundary, or that point may lies inside the region, such that it attains its boundary, it attains its maximum at that point. If that x naught comma t naught lies inside the domain omega t, then just wait. Okay, so if that point lies inside the domain omega t, then this condition is going to be satisfied that Vt plus Lv should be less than 0, isn't it? It means if you are taking the d of v equals to 0 and vt is positive, then for sure this quantity should be less than or equals to 0 to get this inequality, because if this is positive and this is also positive, in that case we won't be able to recover this condition less than 0 inside the domain omega t. So at least this quantity has to be negative. With the condition c equals to 0, I think I am missing something. Just wait. Okay, so I got the point. Here you have two conditions. Either x naught t naught belongs to the boundary, then you don't need to prove that. It is automatically given that we are getting the maximum value on the boundary, isn't it? But if this x naught t naught does not belongs to the boundary, rather than it is coming from the interior of the region, in that case we have to prove that this c should be 0. If that x naught t naught belongs to the interior region, so this condition will hold if c equals to 0. So in that case we are saying that in that case, when x naught t naught belongs to the interior of omega t, then this is going to be 0, and the time derivative of the variable is going to be increased with the time, because the temperature is going to be basically giving the heat. This is basically the heat equation uh, uh, we are heating the rod, so Vt is going to be greater than or equals to 0, because the temperature is going to increase with the time. So x naught t naught, it is going to be positive, the temperature is going to be positive. So what is the possibility? This should be less than or equals to 0. However, in that case we have to take that c equals to 0, because c is a constant variable. If we are not taking c equals to 0, so we have to define sub case that c is greater than 0 or c is less than 0. So to make this condition true, we have to take c equals to 0 when this point is coming from the inside of the boundary. Now, in case B, we assume V x naught t naught is equals to maximum of V is greater than 0 omega t bar.
Excuse me, teacher. What are we doing?
Plus LU is greater than or equals to 0. It's not T naught. Then dt plus LV is less than or equals to minus epsilon. That is a contradiction. It's not T naught is belonging to omega T. With this condition, this is the case, this is the case. I'm stopping this here. We can continue this discussion tomorrow. I'm stuck at some point. I think I need to read that point again. The second case, I think I did it last weekend. I again need to brush up it. So we can continue it tomorrow. Do you guys have any other question?
The homework is going to be at Wednesday or tomorrow.
What? The homework?
Yeah, the assignment.
I haven't given any assignment last week. Do you remember? Because I was aiming to provide you with 12 assignment for whole semester, and I already give you the 8 assignment. So I will be giving the 9th assignment tomorrow, and the 10th assignment next week. Still, we have 2 weeks left. So I will be completing 12 assignment completely. So that's why the last week I did not give you the assignment.
Okay.
Yeah, I have prepared the 9th assignment. I have just to mention the equation and then I will put it there.
Okay.
Yeah. Because 12 assignment is more than enough for a semester. Okay, so see you tomorrow. Bye.
See you tomorrow,
Bye.
teacher. See you
Bye.
tomorrow, all.